In this introduction to slope, we'll look at slope in real life, we'll compare 4 types of slope, and finally bring slope onto a graph. Let's begin by looking at slope in real life. So when you hear the word slope, what do you picture? Some people might picture a hill, like in this construction scene, or maybe a slanted roof. You could think of a sliding board at the playground, or maybe when you hear the word slope, you might just think of a ski slope. Now these are just a few of the many things in life that involve a type of slope. But let's look at these 4 photos. What do all of these pictures have in common? You might say that they all involve something that is diagonal, not straight up and down and not perfectly flat either. Can you see the invisible diagonals in these photos? I'm going to superimpose them here. So you can see the one on the hill, the one on the roof, the one on the sliding board, and the one on the ski slope. These diagonals run in different directions and have different degrees of steepness. Now, how can we describe these differences in direction and steepness in a way that is consistent and useful? That brings us to the mathematical definition of slope, which we'll investigate on the next slide. Let's consider this ramp. I think we all have the intuitive sense that this car is in trouble, more specifically that this ramp is too steep for a car to drive safely. But other than some vague sense that this ramp is too steep, how do we really prove it in a numerical sense? Well, let's look at the hidden diagonal. And what we want to really do is just focus on one chunk of this line that falls between any 2 boundary points on the line. So I'm going to put 2 points on the line. I'll put one toward the bottom and one at the top. And we're just going to look at the part of the line that's between those 2 points. That's called a line segment. Now we can think of this line segment as having 2 component parts. A rise, which in this case is 8 feet, and a run, which in this case is 9 feet. The mathematical slope is the number you get when you divide the rise by the run. Slope measures the steepness of a line by dividing the rise by the run. In this case, the rise is 8 and the run is 9. So the slope would be, as a fraction, simply 8/9, because that's what a fraction is. It's just a division problem. So you could say the slope is 8/9, or if you change that to a decimal by dividing 8 by 9, either with a calculator or by hand, you would get 88 hundredths, if we rounded it to the nearest hundredth, and that would be the equivalent of 88%. Now this last representation is actually the most useful for real life because in the real world application, the slope of a road is called grade and it's measured as a percentage. So this ramp has an 88% grade, and that's way over the limit for vehicle slopes. To give you a comparison, most roads do not exceed a 15% grade. 15, 1-5. In fact, the steepest road in the world has about a 38% grade. So this ramp was clearly not built for a car at all. We don't really even know how this car got on the ramp. And now we can support our claim mathematically that this car is in trouble and this ramp is not appropriate for this car. Okay, so let's look at another common application of slope, building a wheelchair access ramp. Residential ramps must not exceed a 17% grade. Let's calculate this slope. Here's our hidden diagonal. And then remember the order is rise over run. So our rise is 2 feet and our run is 12 feet. And so the rise is relatively small this time compared to the run. And so the overall slope is going to be much less than in the previous example. We'd say the rise over run is 2 over 12, which is just the fraction 2/12. That fraction can be simplified into 1/6. And then when you divide either 2 by 12 or 1 by 6, you would get 17 hundredths, which is the same as 17%. And I said at the beginning, 17% is the limit, so this proves that this ramp is actually a legal ramp. It can be used legally, hopefully safely. So this is the kind of thing that we would use slope for in the real world. Let's return home and look at another aspect of slope. Okay, so in all of the cases we looked at so far, we were mainly interested in the steepness of the diagonal, not so much the direction, but sometimes the direction is important too. And this brings us to our next topic, 4 types of slope. Lines that are rising from left to right have a positive slope. The motion along the line looks as if you're going uphill. Lines that are falling from left to right have a negative slope. The motion along this line from left to right looks as if you're going downhill. A horizontal line has a slope of 0. It's completely flat, and so remember slope measures the steepness, so it makes sense that since a horizontal line is flat, it has no steepness. To put a number on that, we say the slope of a horizontal line is 0. It has 0 steepness. Finally, a vertical line has what's called an undefined slope. Now that might sound a little bit weird. There's a mathematical definition of undefined. It occurs when you divide something by 0, which we're going to see in a later slide will be the case with this line. But you can think of it in the sense of this line is so steep, you can't actually measure how steep it is. It's infinitely steep, and therefore you cannot define it. That might help you remember that a vertical line has an undefined slope. And we'll look at the mathematical implications of that soon. All right, so just to compare and contrast the 4 types of slope, once again, a positive slope is for an uphill line running left to right. A negative slope is what you get on a downhill line running left to right. A 0 slope is what you have on a horizontal line. And on a vertical line, you have an undefined slope. All right, so let's return home, and we're going to look at slope on a graph. First, can anyone predict which of the 4 types this slope will be? This is an uphill line from left to right, so we know it's going to have a positive slope. It will be a number, and that number will be positive. So again, I'm going to section off one segment of the line by putting 2 points on the line. And what I'm going to do is I'm going to always start with my leftmost point, because when you're looking at graphs, you're usually looking in a left to right motion. And so I'm going to always consider the point, and I would recommend that you do this, that's on the left, whether it's above or below. So this one is kind of on the bottom. And what I'm going to do to think about the slope is I'm going to just look with my eyes the rise from that bottom point up until I get to the level of the other point. Once I'm at that level, I know that that's where I will stop counting. So let's count out this slope together. 1, 2, 3, 4, 5, 6. With 6, now I'm at the level of the other point. So 6 is my rise of my slope. Now I'm going to look at my run. 1, 2, 3, 4, 5, 6, 7, 8. The run is 8, and so my slope is 6/8. But I could simplify that because 6 and 8 are both divisible by 2. So after I divide both by 2, I would have a slope of 3/4. Now what's interesting about the simplified version is you can actually think of it as a new rise, 1, 2, 3, and a new run, 1, 2, 3, 4, if you look at that, that will give you more points on the slope that you originally may not have seen. In fact, I can keep using that simplified slope up 3 over 4 and keep counting out new points on the line if I wish. All right, the slope of a downhill line, we expect that this slope will be negative. I'm going to put 2 points on the line. And this time, if I start with my leftmost point, I actually don't have a rise. I have a fall. I'm still going to call it my rise over my run, but I'm going to use a negative number to represent the fact that this rise is actually a drop. So as we count, we'll use negative numbers. -1, -2, -3, -4, -5, -6. I'm at the level of my other point. So my rise is -6. My run is still positive. As I run toward the right, I'm running in the positive direction. That's one benefit to always starting on the left. That means your run is always going to be positive. So my run is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is my denominator, so my slope is -6 over 9. And this simplifies into the fraction -2/3. Now again, this is interesting because I can think of that new numerator, the -2, as my new rise. So I'm going to go back to my original point and watch. I'm just going to go down 2, 1, 2. And that 3 on the bottom is now in the denominator is my new run. So from those 2 green marks, I'm going to go over 1, 2, 3. And voila, we get back to the line. We can put a point on our line. And I can keep doing that over and over using that simplified slope to count. Down 2, over 3, put a point on the line. Down 2, over 3, and there's where that point on the line was. So my slope is -2/3. We said the slope of a horizontal line is 0. This is because if we try to do a rise from one point to the other, there's actually no rise. I'm already on the level of the other point. So my rise is 0, and my run is just whatever the distance is between the 2 points that I happen to choose, in this case 7. But it doesn't really matter what the run is, because 0 divided by anything is 0. A horizontal line has a slope of 0. The vertical line, if we look at 2 points in the line, it does in fact have a rise, which I'll count out as 1, 2, 3, 4, 5. But if we want to run, we actually don't have anywhere to run. Our run is 0. And we get a strange result when we try to divide by 0. The result is actually undefined. You cannot divide by 0 mathematically. Think about it. You can't divide something into 0 parts. So division by 0 is undefined. So I hope you've enjoyed this introduction to slope, and our next video will focus on the slope formula and some more advanced applications of slope.